In this video, I am focused on the lab skills that are typically associated with any Physics 1 course. This is the second of 3 videos in my Unit 1 titled Math Review. If you want to practice what is covered in this video, then check out the video description. You can find a link to my worksheet 1.02, as well as video answers for each problem. Let's start with lab tools. Some of these are referred to as being commonly available, meaning that you are expected to know what these are, how to use them, and when to select them, whether you are physically performing a lab yourself or solving a lab-based question on a worksheet. First is the meter stick. It helps measure length. You want to be in the unit of the meter. Next is the stopwatch to help measure time. You want to be in the unit of the second. The scale, or the electronic balance, will measure the mass of the object placed on top of it. The unit should be the kilogram. Force sensors and spring scales are both used to measure force. You want to be in the unit of the Newton. Protractors help measure angles. The unit is the degree. And then the graduated cylinder will help measure volume, and the unit is the meter cubed. There are 2 other lab materials that are less commonly seen, but certainly possible. The first is the motion sensor. It will measure the velocity of an object moving in front of it, and the unit is the meter per second. Now this has a constraint. It can only measure motion in a straight line path, so maybe not the best choice if your lab is related to something that is curving. Also the manometer. This is sometimes referred to as a U-shaped tube. This will help measure the pressure difference between the 2 ends, and it's measured in pascals. Let's talk about writing a procedure. This is useful when you are designing a lab from scratch, or you are explaining the steps of your lab that led to your solution. I like to think of this as if you were writing an instruction manual to someone else so that they could repeat the lab you are running. What would you include? Well, we'd start with what variables you are measuring and what units you are measuring those variables in, the number of data points you will be taking, and how many trials you will be completing per each data point. I would recommend as a minimum that you would want to take at least 5 data points and at least 3 trials per data point. What lab tools will you be selecting, and how are you going to set them up to ensure that your data is accurate? And when it comes to the analysis of your data, you are likely going to create a graph. You should be considering which variable will be graphed on each axis, and then talk about what part of the graph is useful, whether that is the slope, the y-intercept, or the area underneath the data. Here I'm going to talk you through a sample lab design. Most physics labs are presented as an open-ended question. Maybe my teacher gives me this battery-powered toy car. We know that the car moves with a constant velocity, and the teacher asks me to design an experiment to measure the constant velocity value of this car. First thing I'd want to do is consider which variables to measure and what units to measure those variables in. I'll be choosing position and time. Position is variable x, measured in meters, and time is variable t, measured in seconds. From there, which lab tools will I want to select, and how will I set them up accurately? I will choose the meter stick for position and the stopwatch for time. To use the meter stick properly, I'm going to measure out markers on the floor every meter from 0 meters to 5 meters. And then to use the stopwatch properly, I'm going to release the car at a position of 0 meters. That's where I'll start the watch. And then I'm going to stop the watch when the car reaches each of the other positions. From there, number of data points and trials. As recommended, we want at least 5 data points and 3 trials per point. So we want to make a nice data table like this. Notice I have my positions from 0 to 5, and then I'm measuring 3 times, 3 trials of time, and I want to take the average of those times to get the most accurate time value. From there, how will I analyze the data? I'm going to create a graph of position on the y-axis and time on the x-axis, specifically the time averages. I know that the slope of this graph represents the car's velocity, so if I can take my data, create the graph, and analyze the slope, that should help me determine the value of this car's constant velocity. Next, graph skills. So I have performed the lab. I now have a data table of position versus average times. The first skill is in scaling the graph. Notice that my scaling goes up by equal increments and also lets me plot all of the data points. From there, we want to plot those points. So here are the sample data points plotted. And as shown, your data won't always be on one of your increment markers. That's okay. And also don't expect your data to make a perfect shape, whether that's linear or curved. Labs tend to have error, and your data might show that. From there, a line of best fit. Most graphs will be linear in shape, but again, the error might not give you a perfect linear line. So we'll want to draw a line of best fit, which represents the average slope of your graph. From there, calculating the slope or the area. As mentioned for this particular lab, finding the slope is how we're going to calculate the velocity of the car. So I would use my data and the graph line to find the slope. This comes out to be about 2 meters per second. And now I can write a mathematical model that describes the graph variables, the relationship between position and time. Well, my y variable is position, my x variable is time. The slope is that 2 meters per second, and this object started at a position of 0 meters. That's my y-intercept. Once we write our own mathematical model, we will often need to compare it against a known formula sheet equation. This is a kinematic equation of motion with position versus time. The acceleration of the car is equal to 0 since it was moving with constant velocity, and the starting position of the car was equal to 0 meters, so I can cross these terms out. Look at what is left. Both equations are equal to the position variable. Both have time, and the number in front of time, here 2 meters per second, correlates well with the velocity variable here. So now we can conclude that the slope does equate to the velocity based on the known formula. We might also use our mathematical model to make future predictions. Maybe the teacher asks how long it will take the car to travel 100 meters. I can plug in 100 meters for the position variable and use my equation to solve for time. Another skill is known as graph linearizing. This is useful when your graph data does not produce a linear shape. If we were studying a swinging pendulum, then the period of the pendulum, capital T, is related to the length of the pendulum's string L, according to this formula sheet equation. If I were to graph period versus length, I will not produce a linear shape because of the square root listed in the equation. Well, how can we get the data back to linear? This is known as graph linearizing. The slope-intercept form is the easiest way to write a mathematical model, and that is only available if the graph is of a linear shape. So if you plot your data points, and your data shows a curving relationship or a non-linear relationship, you'll want to linearize the data first. If you see an exponential graph, then the fix is to square the x-axis variable. If you see a side parabola shape, then you want to square the y-axis variable. And if you see the inverse style graph, then you want to invert or do 1 divided by the x-axis variable. Now there can certainly be more than these three, or even combinations of them. I'm just listing these because they are the most common to see. Back to our graph of period versus length, which had a curving relationship, I see a side parabola, and the fix is to square the y-axis variable. So I would regraph my data as period squared versus length, and the data will become more linear than it was previously. And now because of the linear shape, I can use my slope-intercept form to write a mathematical model. Lastly, I'll mention percent error. This is a calculation that you can make to show the accuracy of your lab. These are absolute value bars at either end. The actual value is the ideal value with perfect conditions. Maybe your teacher gave you a known value that you want to compare your lab result against. The experimental value is the value that you recorded from performing the lab. When you plug these in and perform the calculation, you'll be given a value of percent error, and this will analyze how close your result is to the actual result as a percentage. If you found this video helpful, then please consider hitting the like button and subscribing to my channel. You will help me reach more students. For more content videos, tutoring information, practice materials, and live review sessions, check out my website or follow me on my social media platforms.